Hello, ladies and gentlemen. I hope the last two videos worked for you. They were from last year, so we got a current one this year. 1.6 talks about exponential functions and logarithmic functions. We're going to do exponentials today. Tomorrow you will do logarithms. Well, let's do a little history lesson. Have you ever heard of Moore's Law? Probably not. Maybe some of you computer geeks have. Well, Moore's Law says that, and this is 1965, by the way, which is 51 years ago. Every 18 months, computing power and capacity will double. Guess what? That has held for 51 years. Probably won't hold for the rest of eternity, but for now it's accurate. So we're just going to do a little illustration here. Just a quick one. So this will be years. This will be, we'll just call it computing power. Okay, so at year one, year zero, obviously it's zero, but at year one, we're going to say it was one. Okay. What happens in 18 months? Yeah, that's a year and a half. It's going to double, right? What happens in another year and a half? What's going to double to 4? What happens in another year and a half? It's going to double to 8. Can you see the exponential curve kind of happening? We are so deep into this that we have, you know, a computer chip, guys, what you don't understand is literally this big. The processor of a computer. We're in the billions of transistors right now. These things are so dense that those transistors are only like 20 nanometers apart, which is like 1/1000th of a human hair. Okay, so Moore's law is following an exponential curve. All right, so if you want to graph exponentials, a couple things. An exponential has the x in the exponent. Remember how exponents work. X is 0, what's 2 to the 0? It's 1. Anything to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. Remember to always scale. Now you need to also look at the negatives. What is 2 to the negative 1? Remember that negative makes it go underneath, so it's actually 1/2. One-fourth, etc. So, hey, does it ever go below the axis? The answer is no. So we would say as x approaches negative infinity, y approaches 0. Okay, you could write that in calculus as the limit as x approaches negative infinity of y, or we would probably write 2 to the x equals 0. Okay. Similarly, the limit as x approaches infinity is infinity. Okay. All right. What about y equals 1 half to the power of x. Well, that is a reflection. Remember, this is reflection about the y-axis. Okay, so this one is decreasing. This one is increasing. Remember, up to the right, down to the right, increasing and decreasing. And you have your basic graphs for exponentials. Keep in mind, I can move these up and down, left and right, and I can shrink them and make them smaller and bigger. Okay. Quick review on exponent rules. These are very important. Anything to the 0 is 1. Remember, when you multiply, same base, multiplied, you add the exponents. So if I had like 2 squared times 2 cubed, that is 2 to the 5th. If you have exponent to an exponent, that is when you multiply. So 2 squared to the 3rd power is 2 to the 6th. Remember, you have division. Which is a subtraction problem. We can also do the negative exponents. Keep in mind that 1 over a negative can come up. And then we have roots, something like b to the 1 over n, which would be the nth root of b. Because that'd be something like 4 to the 1/2 power. That is the square root of 4, which is 2. That is probably your most important one of the bunch, honestly, because we will use it and use it and use it. All right. And keep in mind, if you have something like 27 to the 2/3, that is the cube root of 27 squared. Okay. If this is a big number, above 10 probably, I suggest rooting it first. So what the cube root of 27 is 3. And then you square it, you get 9. A lot easier than 27 squared cube root. All right, almost there. And then solving equations. So let's say I have something like this. Okay, same base means these have to be the same. So in essence, what we can do is solve here. X equals 4 over 3. Okay. Something of this nature. See how the exponents are not the same. If we can get those the same, though, we're in business. So I'm going to rewrite this as 5 squared to the 3rd, because 2 times 3 is 6. So I know that b is now 5 squared, which is 25. Okay. And then let's do one more, 7 to the 2t plus 1. Sorry, let's just do 7 to the t plus 1 equals 1/7 to the 2t. Remember, get the bases the same if you can. We can. By negating it, you can get rid of the fraction. And then we can set these equal. And I believe we'll get that answer there. Okay. Remember the number E, which is approximately 2.71828. It is very important. It's kind of like pi. It's an irrational number. It goes on forever. No repetition, no patterns. It's very special. Logarithms will make this a lot more clear. Okay, but keep that in mind. We will work with that as much as anything else. So I think that's about it. I'll give you the work. This is 1.6a, 1 through 9 odd, 31. Let's do 1.1, number 57, and 1.5, the prelims, number 4 and 6. Keep in mind that we didn't do 1.5 formally, but you have the information from a different book. Inverses. Okay, so calculate those inverses out. Toodles.